without further ado, hi everyone, my name is Thomas. I'm the product manager on Chrome's web platform team responsible for WebAssembly, as well as V8 and web capabilities. And today I'm going to talk to you all about WebAssembly. And specifically, I want to talk through what is WebAssembly, kind of a brief explanation. Then I want to go and show some of the examples of cool kind of demos that people have built with WebAssembly, as well as some real-world applications that have been built with WebAssembly. Then I'm going to jump into some actual code and show you how you can write some WebAssembly yourself to hopefully kind of demystify parts of the process and make it seem less scary. And then lastly, I'm going to close out by talking a little bit about what the WebAssembly team at Chrome is actually working on right now and what some of the things you still have to look forward to with WebAssembly. So what is WebAssembly? WebAssembly is a new low-level binary format for the web. It's compiled from other languages, which means that you don't actually write WebAssembly yourself. Instead, you take something like C++ and compile it into WebAssembly. And because you compile it before you ship it over the wire, and because of some of the characteristics of the language, it can offer maximized performance compared to JavaScript. That being said, though, it's important to note that WebAssembly is in no way a replacement for JavaScript. Instead, it's supposed to fill the gap on the web that JavaScript today doesn't meet.
Why is there a question mark?
That's a good question. It's a typo. I wrote that sentence like 3 hours ago. All right, that's number 2 thing that's gone wrong. Is anybody keeping count? OK, so talking about WebAssembly, why you would actually use it in the first place. As I already mentioned, one of the main reasons is optimized performance. JavaScript is a dynamic language, which means that it's actually optimized by the JavaScript engine in the browser as you're running the JavaScript itself. Contrast that to WebAssembly, which you compile on your developer machine and then send that compiled and optimized version across the wire. WebAssembly as a format is also much closer to the CPU machine code that your computer understands, and that allows you to get this much more reliable and optimized performance. Secondly, WebAssembly offers amazing portability. Because you can compile from other languages, you can port not only your own applications or code that you've written in something like C++ to the web, but you can also take the immense wealth of open source libraries that have been written in the past and then bring them straight to the web very easily. And we're going to show you some examples of that. And because C++ specifically is supported on practically every platform, including iOS and Android, you can set up a developer environment where you write in C++ and then have export paths to all of your surfaces that you want to reach. Lastly, and potentially most exciting to many of you in this audience, is the promise of more flexibility when writing for the web. Since the web's inception, JavaScript has been the only option as a fully supported runtime if you wanted to do any logic as part of your website. Now with WebAssembly, you can take other languages, specifically C, C++, and Rust today, and compile those and run them in the browser. C, C++, and Rust are the ones that are currently fully supported today, but there are many other languages, including Kotlin and .NET, that are working on support for WebAssembly and have already shipped experimental versions for you to play with. OK, so that was a little bit about WebAssembly and why you want to use it. I want to take a little bit of a tangent, I hope you'll let me, into exploring why you'd actually want to do higher performance demanding logic on the web and why you'd actually want this. And to me, it's all about enabling the web to do more. Here is the world's first website. It, as you can see, is very slightly formatted text with some blue links that you can click on. At its inception, that's really all the web was. There was no logic, there was nothing. Then this thing comes along. JavaScript, and now suddenly you can actually create logic on the web and have interactions that are more complex. And this was kind of when you started to see some of the first real web apps, right? Like applications that you interact with in the browser. Gmail was one of these first ones, but there were many others like MapQuest and eBay that had some scripting logic. And as interest grew in kind of doing more on the web, we see this moment where suddenly there's an explosion of libraries. These are things like jQuery, Angular, DB, 3JS. Obviously, these came out over a long period of time, but they were ways for a developer to take a piece of functionality that they wrote and then share it with others who could then use it themselves, I think that's a really underrated power. And when you think about the things that you can accomplish with these simple frameworks without having to know all the gritty detail, I think that's really amazing. And as interest kept building in doing more on the web, the browsers eventually responded by actually improving what you could do on the web. We had things like V8, which revolutionized JavaScript performance and actually made it viable to do things on the web that were even slightly performance demanding. In a similar vein, we had WebGL, which now brought 3D graphics to the web. And then also things like HTML5 and now, very recently, service workers. You see browsers embracing this idea that we should be doing more difficult things on the web. But why? Why have we actually been doing all these things? Why have we been progressing down this path of a more capable web? Why don't we just leave interactivity to the native operating systems where developers have full access to everything and they don't have to worry about being restricted in some way, either to language or to capabilities? Well, there are actually 3 things about the web that make it a shockingly great place to have applications. The first of that is linkability. I think this is maybe the most underrated superpower of the web, but this notion that you can take a single string and regardless of where you are, regardless of how you transport that, share it, you can click that in almost any piece of software, whether or not you're looking at a PDF file on Linux or an iOS app. If there's a blue link, I can click on that and get to a piece of content. Secondly, the web application is ephemeral, which means that you don't have to worry about the process of installing it or whether the application is trustworthy. I, as a user, am never scared of going and clicking on a link the same way that I'm terrified of downloading an exe. And lastly, the web is the only truly universal platform, meaning that your application is accessible by anyone, any device, any operating system. This also means that as a developer, you can maintain a single code base and reliably ship to every platform. And so that finally brings me back to WebAssembly and this idea that it empowers you to do more difficult things on the web and makes it much more of a real platform for absolutely anything. And that vision and that goal is why all 4 browsers came together to create WebAssembly. And it's why WebAssembly is now shipping in all 4 major browsers, making it the first runtime since JavaScript was created over 20 years ago to be shipped in every major browser. OK, so now we're going to jump in and actually look at what some of the things you can build are. I want to start out. I have a couple of examples, but this one I want to make a plug for because it's a pretty cool demo. This is the Chipmunk physics engine. That's the one utilized by Cocos 2D. We've taken it and compiled it to WebAssembly and then hooked it up to a bunch of SVG elements. Every little bead is actually an SVG element running on the HTML page with all of their interactions mediated and controlled by a WebAssembly module. So that was one example. And the reason why I plugged this as part of a slide is because if you go to this URL, we actually have a code lab that walks you through how you can port the Chipmunks library and how you can incorporate it into a web page. But now I'm going to try. All right, this is the really scary part where everything is going to go wrong again. But I think I see my cursor. OK, so I'm, by the way, looking up, which is why this might seem kind of weird. But I wanted to just show off a couple of examples. This is one project where somebody has taken PDF renderer, brought it into the browser, and now I can do all kinds of fun scribbles. This was a project by, I think, 1 or 2 people. And it's a really sophisticated application. But if you actually dig in, a lot of it was already written by teams worth of people. And because it was open source, developers were able to just take it, bring it into the browser, create a little bit of UI around it, and suddenly have an incredibly powerful application. The other example that we have is this one, which doesn't work nearly as well, given that I'm looking up at the screen. But this is a video manipulation, where it's actually taking a live camera feed, and I can apply all kinds of fun effects kind of in real time. Doing this kind of video editing in real time is incredibly computationally intensive. And video is something where you don't want to have sudden breaks and pauses. And so that's another great use case for WebAssembly. And then everyone's childhood dream, Pokemon, and running that in the browser. This is a Game Boy emulator written by someone in this audience. Where are you? Raise your hand. Over here. If you want to talk. Yeah, all right. Round of applause. Enabling my childhood dream of playing Pokemon. I was one of those kids whose parents wouldn't let them have a Game Boy. So yeah, this is very special. So you might ask, okay, well, how crazy does this get? What kind of software can you actually compile? Well, someone was crazy enough to go and take Windows 2000 and compile the entire thing to WebAssembly. So now you have an operating system running in your browser. This should be terrifying to everyone in this room, but one reason that I hope you'll be excited, or at least that I was excited, was because this specific operating system had one very specific thing that I always loved, and I've set this up. Hopefully, now I can actually read that. What does it say? Oh, I thought it was going to do the bounce thing. Was that only a thing in later operating systems? Damn. All right, well, clearly I should have tested that. But you can go. Does anybody remember playing the pinball game? Yeah. I won't take the time to actually load it up, but this is out there. You can search for it and go and play pinball yourself. I definitely lost some time playing that. Turns out that there are more than one person out there who is a little nutty about compiling operating systems. Turns out that one of those people also really liked WebVR and decided to make a simulator where you can pretend you are in a 90s basement running this thing. And now in here, I can actually click and interact with this thing that's rendered. I can't see my cursor well enough to do it from here. But trust me, this is an actual operating system running on a canvas tag inside of a WebGL-enabled environment, all hooked up to WebVR so that you can actually put on a headset and pretend you're in the 90s. All right. Yeah, all right, yeah. So that was, those were all hilarious demos, but probably not too many of those are products that you actually want to ship. And so to prove that WebAssembly is, I swear, useful for other things than compiling Windows 2000, I wanted to just walk through a couple of other real products that have actually already shipped WebAssembly to thousands and thousands of users. One of these companies is Figma. Figma is a design tool that works in the browser. It has the same kind of collaborative editing that most of you are probably familiar with from systems like Google Docs. And this is really powerful because it shows off that you can have that same model that works so well with Google Docs of being able to share links, rely that people can access the application and the document, and then also have that multiplayer collaborative editing. And it works really smoothly, even for something that's as complicated as a design piece of software. With native design tools, you have to worry about managing the right file, whether everyone has the right software installed on the machine. If I'm sending them a file, are they going to be able to open it? And whether or not, if I was sending a file to someone, whether or not the application that we were using even supported their operating systems. Now, with the power of links as the single source of truths, you can send around links, share them with anyone, and rely on them being able to access it instantly. I wanted to very briefly mention kind of how Figma set up and architectured their application. They have a few different components. The first is kind of the surrounding UI, like the menus and things like that. And they've implemented this in a TypeScript and React-based system. And then the center kind of area of actually editing is all enabled by C++ / WebAssembly and is run in just a canvas tag. And this has a couple of different components. There's the custom rendering engine that they've written themselves in C++ compiled to WebAssembly. And this is the one that actually decodes the file format and displays it. They've also leveraged WebAssembly's portability and taken open source libraries FreeType and HarfBuzz, compiled them to WebAssembly and utilizing them for their text editor. And then lastly, they're utilizing WebSockets to get that dynamic multiplayer editing. And so you can see that by architecting their application around these different powers and using these advanced technologies, you can create a really smooth experience. Another example that some of you might have heard of is AutoCAD. I love this example because they took a 35-year-old code base, a code base that literally predates the internet itself, and compiled it to WebAssembly 100% running in the browser. And similar to, that's not showing what it's supposed to. Animated. They have a very similar setup, surprisingly similar, also a React and TypeScript enabled kind of surrounding UI with a central canvas element, and then also a JavaScript and WebAssembly message passing API so that they can communicate. All right, so now let's see some actual code. Hopefully all of those crazy examples got you like excited, like, all right, I want to go actually write some WebAssembly. Let's see how it works. The first thing to mention is WebAssembly's amazing toolchain, Emscripten. Some of you may know Emscripten when it was used to turn C++ into Asm.js, which was a precursor to WebAssembly. Emscripten has since morphed into a fantastic toolchain for WebAssembly. It's what you'll use to compile your source files into WebAssembly, but it also does a ton more for you. It offers a lot of automatic translation, such as translating your OpenGL calls into their WebGL alternatives, and it even emulates an entire file system for your ported application to use. It also includes the C standard library compiled to WebAssembly, so you have all of that functionality right out of the box, and some additional build tools to replace things like configure and make. You can read all about Emscripten at emscripten.org. All right, so let's take a look at some actual code. This is the computational equivalent of hello world. It's calculating the nth Fibonacci sequence. And you will notice two additional lines that you probably aren't familiar with at the top, include emscripten.h and emscripten keep alive. The first line includes the Emscripten library, which is necessary for Emscripten to work on your C and C++ code. And then this second Emscripten keep alive tag lets Emscripten know that, hey, this function, I'm going to be calling it. If it looks like I'm not using it, I'm telling you, don't get rid of it in dead code elimination. This is the terminal command that you'll actually use to compile your WebAssembly. And let's step through each piece. This emcc executes the actual Emscripten compiler itself. And then we pass in -s wasm equals 1 to make sure that it'll output WebAssembly as opposed to Asm.js. And then we name our output file, in this case -output fib.js. And then finally, we give our input file. emcc will give us back two different files, a fib.wasm and a fib.js. The fib.wasm file holds the minimal WebAssembly binary for our actual compiled C++ function. And fib.js holds a lot of kind of helper glue code that's in JavaScript that helps us load our module and interact with it. It's worth mentioning here that Emscripten has a ton of different ways to actually output this code. You can pass in, for example, requesting an HTML file, and it'll give you back an HTML file with a terminal simulator that you can actually use to interact with your WebAssembly code. There's a ton of stuff here that I definitely don't have time to go over. You'll hear a little bit more about it in some of the other talks, but really emscripten.org and surrounding documentation is the best way to learn about this stuff if you want to use it for a real production application. Okay, so let's actually load this into a page and see how that's done. This is our index.html page, and you'll notice the first thing we do is just include our fib.js, which is our helper file created by Emscripten. And then inside this script tag, we'll actually we'll actually call into our function. This module object is one created by Emscripten and loaded by the Emscripten glue code. And it has a ton of stuff. Again, read all about it at emscripten.org. But one function is on runtime initialized. That's basically once I'm done. And then what we do is we use the CWrap function, which is, again, a special function provided by Emscripten. There's some magic going on here. To say, hey, this function, I want to return a number and pass in a number. And then it gives us back a function that we can easily call in a console.log. And we can find out that the 12th Fibonacci number is 233. If you want to look into more of the documentation about CWrap, you can go to bit.ly/emscriptenc to WASM. OK, so that was great. But as you might have noticed, all we were really doing is just calling a single function and not really interacting with the DOM or any other parts of the web. And so what would we do if we wanted to create this thing? I don't know why you would ever want to create this thing. But in case you do, and in case you want to do it with WASM, we're going to learn how. So this time, we're going to use C++ instead of C, and we're going to have our ball.cpp. Again, we'll include our emscripten.h at the top. And then this function might strike you as weird, or at least I hope it strikes you as weird, because we're inside of a C++ function, but this is JavaScript code. The reason why this can work is because of emjs. This is another magical helper function from Emscripten. Again, you can look up the documentation, but the way that it works is you pass in the return type, the name of the function, and then the inputs. And then inside of this function, you can write just JavaScript. And when Emscripten goes through and actually compiles it, it'll put all the things in all the right places and work out everything for you. And now, inside of your actual int main function, you can just call that function draw circle, passing in the numbers, and Emscripten takes care of all the type conversion for you. So let's look at how you actually compile that. Again, we're going to use emcc. This time, we're going to make it a little bit more complicated, a little bit more optimized. We're going to pass in -03 to tell Emscripten to optimize aggressively, including the removal of unused code. And because we're removing unused code, we have to explicitly say, like, hey, that CWrap function, I'm going to use it. Don't take it away from me. And then because we put our C++ initial function, because we called it main, Emscripten knows to go and execute that on startup. And so we don't even need any code at this point to actually load that module. We just load our helper file, and then that one knows to call the main function. And when we do that, we end up with the ball, which is great. But as you might have noticed, we haven't actually really written any C++ code to do anything yet. We're just calling some DOM commands to draw a red circle. Well, let's actually do something a little bit more interesting. The first thing we'll need to do is actually clear the canvas to get the animation to work. And so we have this clear canvas function, again, using emjs, all the same things. And now we want to do something actually interesting. And so anytime I want to do something interesting, I always start with math, because math is great. So we include math. And now we want to track time, so we include a time variable. Now we actually want to create a C++ function that does something. We'll name it update. You'll notice that we have Emscripten keep alive, as we needed in the last couple of examples. But you'll also notice this extern C wrapper that we put around the whole thing. This is a little complicated, but basically what this does is prevents Emscripten from name mangling the function, and means that when we want to call this update function, we can call it by its original name. Inside this function, we do some simple C logic, basically using the sign function from the math library, and kind of getting it to move in that weird circle way. Then in index.html, we again set up our module with a pre-run function that once again, this same as the last example, uses CWrap, calls into our update function. Again, we can use the string update because of that extern C wrapper. And then we can request the animation frame, and what do you know? We end up with a weird ball spinning for some peculiar reason. All right, so that was it for the code section. You're going to get tons more code examples to look at in the future talks. But I wanted to close out my talk by talking a little bit about what we're still working on. One of the things that's probably the most exciting for us on the WebAssembly team is threads. Modern CPUs ship with several cores, but historically the web has had very limited access to these additional cores, restricting how performant your application could be compared to native. You get some additional access to these cores through things like web workers, but web workers can be quite heavyweight, and because they rely only on post message for communication, that restricts the kind of use cases it can be enabled for. WebAssembly threads will use something called shared memory, which will allow different worker threads that you will just instantiate with classical pthread type syntax to actually rapidly share that memory back and forth and really allow you to do fully complete threaded applications on the web. We are also changing how WebAssembly interacts with the rest of the web platform. Today, when you want to access a piece of web functionality like talking to the DOM or calling a web API like WebGL, you actually have to call out to JavaScript, and then JavaScript makes the call on your behalf and then sends the message back to WebAssembly, which is less than ideal, especially for very high performance demanding use cases. And so we're changing this so that WebAssembly modules can actually hold references to these things directly and avoid having to go through the JavaScript layer. Yeah. Looking a bit further ahead, we've also started exploring direct ES module support for WebAssembly. This will improve the ability for WebAssembly and JavaScript to import and interact modules of the other type without having to do any unnecessary wrapping. Together with letting WebAssembly hold references to the DOM and web APIs, we're dramatically improving WebAssembly's interoperability with the rest of the web stack. All right, so also further out is support for additional languages. You heard me mention before that C, C++, and Rust were the kind of fully officially supported languages. And the reason why they are is because they're the ones that manage their own memory and don't have what's called a garbage collection system that does it for them. As I mentioned, though, there are some languages that use garbage collection, including Kotlin, .NET, and Go, which are experimenting with support for WebAssembly. And the way that they've actually done it is that they've taken their garbage collection system and their runtime and actually compiled it to WebAssembly, shipping it along with the page and letting it execute and manage all of the memory. There are a lot of spiky edges around these languages, though. They are still considered experimental. And unless you have strong confidence in your use case, an understanding of how these works, they're probably best reserved for kind of experiments and playing around, although they can be extremely powerful for that. We're working on kind of first-class support for these languages, actually changing the WebAssembly spec itself to enable these kind of garbage collection systems to properly interoperate, though I'll caveat and say that that's still probably more than a year out in terms of timeline. And with that, brings me to my end of my talk. I think we had a full 3 things go wrong by my count, so like that's not bad. Yeah.